I'm Tim Ventura, and we're joined today by Dr. Matthew Gill, a nuclear engineer turned rocket scientist and all around radiation expert. Dr. Gill is the founder of Space Radiation Services, a radiation testing and analysis company, and his career includes past roles, including engineering, consulting, and research positions at organizations including Astra, Apollo Fusion, Sellafield Energy, the UK Office for Nuclear Regulation, and Rolls Royce. Dr. Gill has a master's with honors and a PhD in nuclear engineering and multi-disciplinary doctoral training in nuclear research, science, and technology from the University of Manchester. He joins us today to talk about radiation. So, Matthew, welcome. Our focus today is space radiation, which you have unparalleled expertise in. And I think the best place to dive in with is actually your current company. So what do you do over at Space Radiation Services, and what types of organizations use your services?
First of all, thanks for having me. This has been a lot of fun thinking about this, and it's a subject I'm really interested in and talk about a lot. So getting to do this is great. So Space Radiation Services primarily focuses on radiation testing and analysis for satellite systems, mostly electronics, a little bit of materials. It's quite a niche area, and it's not the most intuitive area for people who are new to it. Mechanical, electrical, there's a lot of intuition around that, whereas radiation, people kind of struggle. And in most companies, you don't really need a full-time person to focus on it. So that's kind of why I step in. I help people get up to speed, whether it's finding parts that already have radiation test data, whether it's kind of helping people test, understanding the impacts, essentially getting people up to speed so that they can be more sustainable themselves rather than having to depend on an outside source such as myself, or having a full-time hire that they don't really need all the time for that kind of area. In terms of organizations, it's most of it is around, new space companies and startups, but we work with kind of everyone from satellite manufacturers, component manufacturers, all the way up to some of the larger kind of mega constellation providers doing a range of different work, mostly radiation based, but also other things that tie in like reliability analysis and things like that.
Okay. Well, and so you mentioned new space startups. From an industry perspective, I wanted to ask what the latest trends are in space radiation testing, because things are changing. The space industry is maturing. New space companies like SpaceX are entering the market, and small sats are becoming more prevalent. There's just a lot of change that's happening in space. How does that affect radiation testing?
So it's had a big effect. I mean, one of the bigger ones is it's quite hard to get into some facilities these days. They're really oversubscribed. These aren't things that exist all over the world. There's, tens of different facilities. And the big trend that's happening right now is, there's been this CubeSat revolution that happened, and, people making cheap satellites and doing demonstrations. And for a lot of that, they didn't think about radiation, which makes sense. There's cost, schedule, risk associated. You can take more risk. A lot of those companies are now basically building bigger spacecraft because there's more demand for it. Their customers want more capabilities, bigger spacecraft, more stuff going on. And as they do that, the prices are slowly going up. And as the price goes up, people or their customers generally want to have a bit more of an understanding of the reliability, and they want some kind of radiation data. And they don't want to go old school, like, the heritage approaches where everyone tests every single individual component like separately, done to certain mil standards. Just because it's all using radiation hardened parts, which you can buy, which are very expensive and long lead time, because, that kills schedules and that kills kind of their cost. So they're willing to accept kind of a slightly like higher risk to try and drive down the cost and schedule, but they kind of want to have a balance there. So it's a lot of companies are trying to figure out where they fit in that. How do they make costs and schedule match and risk, and like what kind of level of radiation they do, because there's no real testing standard for new space, and people are all figuring that out. So the main thing is new companies trying to work out what their kind of middle ground is. That's the big one. And the second thing is more people going to new orbits. There's been a lot of satellites going into low Earth orbit. And now companies are looking at, higher low Earth orbit, MEO, GEO, and cislunar, as well as like interplanetary stuff. And the radiation environments are different. And, in LEO, you're protected to some extent. But as you kind of climb a little higher from those kind of common SpaceX rideshare missions at 500 kilometers. As you go higher to more like 1,000, things change quite a lot, and it's a really sharp ramp up. And people aren't worried that their devices are going to fail instantaneously. They're not just going to take them down; they're going to explode immediately. That's really unlikely. The big concern is you have other effects like bit flips in memory, or you have a radio reset. And at 500 kilometers where people have been operating, that's happens every month or every year, and that's not a big deal. Like if you think about your computer resetting every year, it'd be annoying, but it wouldn't kind of kill your productivity. And in some of these higher orbits, it's happening more like 10 times a day, which makes operations really difficult. So those are things radiation-wise which cause really big concerns for people as they get onto orbit, as well as kind of the total lifetime. So those are the big two trends, really. It's kind of things getting bigger and some sort of testing needed, and people going to new orbits where it's getting a little trickier.
Ah, well, and again, what you do and the effects of radiation are really important in space, and I think often overlooked. But let me back up and do a quick primer for anybody who slept through science class in school, or maybe the more appropriate way to say that is radiation is something that probably everyone in space science has learned about. But again, it's something that we overlook, we tend to forget about. And so I want to kind of back things up because I have a really diverse audience. Radiation is all around us from a variety of natural and artificial sources. We're constantly exposed to it throughout the day. So the danger to humans and equipment is not exposure itself, because we're all picking up some radiation all the time. It's basically about getting too much, right?
Yeah, getting too much and that kind of exposure. So, you know, on the ground, radiation effects are kind of very minimal, and health to humans is kind of low because your body's able to regenerate and protect yourself. When you get to higher dose rates, especially in places like the nuclear industry, it's when your body is not able to kind of fix any of the damage that happens. In terms of electronics and space, that side of it is more that the buildup of radiation causing slow degradation and failure. But there's also another side of it where these kind of instantaneous effects, there are very high energy particles coming from the sun and galactic cosmic rays. And they're the things which, happen at random, and they can cause bits to flip, parts to reset, high power states in devices which shouldn't see them that can cause failures. So in space, there's also kind of a probabilistic standpoint as well as that kind of slow kind of degradation. And on the ground, you don't worry about that as much, but there are some areas where you do worry about those kind of instantaneous random effects. In data centers, if you think of those things on the ground, because you have the Earth's atmosphere protecting you, they're very low frequency and very low probability. But if you have a huge data center, low probability things are happening all the time. You have tons of memory, tons of processors. And a similar concern is coming up with self-driving cars as well, because, if you have every single car being a self-driving car, 1 in a million events are not acceptable in cars driving around on the road where something could switch off and stop working. That would be terrible. So they do affect some of the sort of day-to-day things and will be coming up more. But in general, on the Earth, around where we are, it's not the biggest concern. It's just getting worse, when you get into space, basically.
Yeah. Well, let me kind of break this down in a way that makes sense to me, and hopefully this is correct. Again, humans evolved on the ground, which is protected from most radiation by the atmosphere, as you mentioned. We build our equipment on the ground primarily, so it's kind of designed for that environment. The higher you go, the more radiation you get. So airline crews, I think most folks are familiar with this, they get more exposure over time. In low Earth orbit, you're getting a higher dose, but you have some protection from the Earth's magnetic field and partial shielding from the Earth, right? And then further out, you're getting this mixture of cosmic rays, high energy particles from the solar wind, and just a lot of hard UV and maybe X-ray and stuff like that from the sun, right?
Yeah, that's exactly right. Once you get outside of the Earth's magnetic field, you kind of have exposure to everything. And the Earth's magnetic field is kind of a bit of a blessing and a curse for spacecraft as well. It protects when you're close to the Earth, but once you're in it, the magnetic field captures all of these charged particles. So it's like a high concentration. So some of the worst radiation environments are essentially in those belts, and it can be kind of a concern for MEO environments.
Well, and actually, I was going to come back to that later, but what I want to ask first though is, your company helps ensure that equipment is radiation resistant by doing this testing. So, one thing that I really wanted to ask about was, does that mean that you're actually generating radiation exposure to equipment? And do you have to simulate different types of exposure depending on where the satellite or space vehicle will operate, right? Because again, at different altitudes and in different environments, you get different types of exposure.
Yeah, yeah. So one of the big problems is that you can't generate on Earth exactly what you're seeing in space. So we typically use kind of analogs. So if you imagine, galactic cosmic rays and what's coming from the sun, you have almost every element in the periodic table flying at super high velocities in different quantities and going through your parts. You can't really do that on the Earth. Like you have big cyclotrons, but and things like CERN, but they're still not giving that mixture and all of those different environments. So we use kind of analogs. Maybe we're using fewer particles that are heavier and lower in energy. We play those games and make those kind of like associations, basically. And it does mean that you don't have to change the way you radiation test to get an idea of different orbits. You can kind of do a specific suite of tests which will cover you, but you do have to kind of extrapolate and model that differently to your different environments. But yeah, that's spot on.
Ah. I also wanted to ask if you do consulting on how to radiation harden equipment. For instance, manned Mars missions are likely going to pack supplies around the crew capsule to help absorb radiation. And from what I understand, they're actually planning trip lengths to minimize exposure as well. And then I've read that microchip design and packaging is sometimes different to account for radiation in space as well. So, are those things that you do consulting on and you help companies with?
Yeah, yeah. As much as you can, you try to get away with doing, as little as possible to the design and architecture of your electronics. So if you can just throw more material around there and shield it better and protect from radiation, that helps a lot. So a lot of the work involves kind of, doing some testing and then working out how much material you need around the outside to try and protect those parts. It's definitely a lot harder for people, and I generally try to stay away from that. After working in the nuclear industry, where everything was, focused around protecting humans. It's a good way to slow projects down because it's so important. So I try to focus more on the things which don't involve humans because it's just so critical. It's kind of a little terrifying and it can be a much slower pace. But I can believe that trying to package things around spacecraft going to Mars to try and shield humans makes the most amount of sense. And cutting those journey lengths down is going to be the biggest thing. Time and shielding are the two things you have. So if you can kind of do both of those things, you've got to.
Yeah. Now, so in terms of manned missions, the light flashes and streaks seen by astronauts, and again, I'm trying to use something that I think a lot of people have read about or seen shows about. Um, those have been attributed to high energy, heavy cosmic particles passing through the eyes. So, a new report concludes that short term exposure is not a serious hazard to these, but for long term missions, I mean, basically, this is like a shotgun blast at the cellular level, right?
Yeah, yeah. I mean, it's basically it's destroying cells, it's destroying DNA, and if it happens, not too much, you don't get a very high dose. Your body can essentially repair all of those things. If it happens too much, you can't. It overwhelms you, and you start to have like real issues, and that's why people end up with cancers due to radiation exposure. Like in space, that's a concern, and you mentioned like the streak through your eyes. Eyes are very sensitive to radiation, but interestingly, there's kind of people aren't sure of the mechanisms behind a lot of this. There's kind of a linear approach where people say any amount of radiation exposure will proportionally increase your cancer risk. But down here, kind of close to the beginning, it's kind of in the noise. Whether you have enough vitamin D or drink too much coffee will probably have as much of an impact as other things like that. The other theory is like there's an onset threshold. So your body can repair up to a point, and then once you get to that point, your probability of getting cancers and things starts to increase. And there's a third one, which is extremely hard to prove, but it's kind of an interesting concept, is that actually with small radiation doses, your probability of getting cancer actually goes down before coming back again. And that's to do with the theory being that the radiation will actually stimulate your body to actually protect itself. And it finds things which are broken that it wouldn't already have found with DNA and cells, and actually reduces the chance of you getting cancers. But again, like that's I'm not saying you should go and irradiate yourself to try and improve your health. It's in the very much in the noise that things will affect, things like I said, drinking coffee, vitamin D, stuff like that will probably have as much of an impact, but it's kind of a novel way that people don't quite understand because there's so many other factors happening at low radiation doses.
Well, and so people do have some self-repair abilities. Equipment does not. And transistors and modern microchips measure nanometers in size, and they get smaller with each new processor generation. So, in terms of radiation, if this shotgun blast wipes out an active transistor, data is lost, bits are flips, data is corrupted. You already touched on some of that before. Is there a way to compensate for that? Is there error correction that can assist with that, or is it just come to packaging and shielding?
Yeah, no, that's a really big problem people have is, there's lots of other things that can happen, but losing data and stuff like that is problematic. And there are ways around it. A lot of modern processors have built-in error correction codes that you can run. And basically, if you have a single bit flip, it can correct it. If get a really big hit of radiation and it flips two things at once, it can't. It'll tell you it's happened, and then it'll just get confused, and you have to kind of go back and check things and redo your operations. But yeah, there's error correction codes. There's even more complex things like some people use triple modular redundancy, where you're essentially doing three things at the same time, and you're trying to check that they're all the same. If one's off, like, that's off, let's do that again, basically. And so there are different ways you can do that. And there's also methods where people have spare copies of memory for important things. They call it having a golden copy, of things which are, more tolerant memory, where you can store that and you can check against it and see if anything strange has happened with really critical data. It's much harder for things like power devices where you don't get loss of data, you get things like basically catching fire. So it's much harder for things like that, but there are other kind of approaches you can take with, running high voltage systems at lower voltages and playing different games like that. But it gets harder with things like power devices.
Well, now I want to touch on, you'd mentioned magnetic fields a moment ago, and we've been talking about shielding. I wanted to touch on huge swarms of electrons in the Jovian system that are accelerated to nearly the speed of light by Jupiter's magnetic field, which is something that I had been told about years ago. And at the time, I had no idea. The person who was telling me about it said, yeah, we have to shield probes that are going near Jupiter because they pick up enormous amounts of radiation. So when I was reading about this, this was about the Juno probe. They have something called the Juno radiation vault, which I guess is a titanium box that they've put most of the computers and electronics into for exactly this reason. So are you familiar with this at all? Can you tell me a little bit about some of the challenges with planets like this?
Yeah, I'm familiar. I mean, I'm familiar. I haven't worked on things like this. Sadly, there's not a lot of work in kind of radiation testing for Jupiter. There's not enough stuff going out there. But yeah, it's a really interesting topic. So Jupiter has a really strong magnetic field like around it, similar to the Earth's magnetic field, but way stronger and larger, basically. And that means that I think I mentioned before that some of the worst radiation environments around the Earth are in that magnetic field where it traps those particles. And Jupiter does the same, but orders of magnitude higher. So if you can imagine, like, a lot of people don't want to be in certain orbits around Earth. You don't really want to go near Jupiter. It's terrible. And that box, yeah, that's how they get around it. Is as much as you can try and build and design electronics to be radiation tolerant, there's a fundamental limit to that eventually. And basically the way around it is you just put huge amounts of mass around it. I think it weighed 200 kilograms, the box they put everything in. It's a great solution for Jupiter. It's not something you can do in everyday kind of life and applications. Like, mass is expensive to get in orbit, but in terms of simple solutions, like it's a great solution. Just put more material around the outside if you can. Yeah.
Yeah. Well, so again, electrons around Jupiter, yet another type of radiation exposure that I've heard of is bombardment with hydrogen and helium nuclei from the solar wind. And I've actually been told stories that some of the long-term space station projects took enough damage at the molecular level from basically these atoms that were streaming out from the sun that they actually had trouble over time maintaining pressure. The air would gradually leak out of billions of tiny little holes. Have you ever heard anything about that?
Not so much about that, but like I mean, it is a big problem having the solar winds have a really big effect. Like flares, they're not consistent. They're very time dependent. You get flares at different times. There's some cycles to how they happen, but they're at different points. And one of the incredible things it does is like when you have big solar flares, it makes the Earth's atmosphere expand, which is kind of fascinating. That has a huge effect on things like, the space station, which has a lot of drag. It struggles to stay up there if you have like the Earth's atmosphere expanding more. And the really famous case recently was the Starlink satellite launches, where they launched one during a flare, and they were basically in. I think the description people said was like it's more like soup than being in space, and the drag brought them down really quickly because they couldn't kind of deploy and get the propulsion systems working fast enough to be able to kind of climb back out of that. And that's something that's like people are thinking of more and more now because we're in a point where the solar cycle is like increasing. So we're going to have more solar events. The Earth's atmosphere is going to expand a bit from time to time. It's going to cause more drag. It's going to cause more radiation effects in the particles that are out there, and other things to kind of low Earth orbit satellites. There's another effect called atomic oxygen, and basically that kind of erodes certain materials down when they're in quite low Earth orbit. So there's a range of things that happen which aren't always like intuitive, and even people like SpaceX kind of get it wrong from time to time. There's a lot of stuff going on.
Well, for me, the question of collisions with high energy electrons, hydrogen, helium nuclei, and atomic oxygen, as you mentioned, all of these present a major challenge for high speed interstellar travel. And I've read that if you're traveling at even a fraction of the speed of light, the effect of all of these particle collisions is basically similar to being inside of a particle accelerator. Do you think that there's truth to that?
To some extent, definitely. I mean, the thing is that what's actually happening with particles in space and radiation is like it is like a particle accelerator already. So if you're moving fast, maybe you're making things a little worse, but it's not going to completely invalidate a lot of those problems that you have. It might make it worse depending on how fast you're traveling, but it's definitely something you have to factor in. I mean, a bigger concern would definitely be they call them micrometeorites. If you imagine if you're traveling that fast and you hit a grain of sand, the amount of force is huge. I'm sure people have seen pictures of what it's like when small particles like collide with the outside of the space station, like the ballistics and like the huge dents they cause are massive, even for really really tiny particles. So if you're trying to do interstellar travel and travel that fast, like a big thing is like if there's just a grain of dust in the way, it's going to cause a huge effect to it. So there's a lot of things you have to factor in.
Yeah. And I was thinking about this last night. In the past, Dr. Kevin Newth mentioned that the majority of exposure in high speed travel is going to be from the front of the craft, which means you might be able to pack consumables towards the front to reduce exposure to this. Um, Another idea might be hollowing out asteroids or using some kind of natural heavy rock material to protect the crew, and I was trying to think about, what are some interstellar travel methods, I guess, to reduce this exposure? Because it seems like as we begin to look at traveling into the stars, this is going to be something that's more and more important over time.
I definitely think there's going to be lots of problems trying to do things like that. I mean, getting technology that can do that in the first place is going to be a big step. But I mean, trying to think about some of these other factors is going to be like concerning. Radiation is one thing, and I definitely think you have to get creative with like how you're going to do these different things. Humans aren't designed to travel that fast. It's going to be there's going to be a range of things we have to deal with. Radiation, micrometeorites, whether that's trying to spin out and move like move different large objects to help you shield it and try and do something creative rather than having to put up tons of lead into space. Like maybe that's the answer. But I think it's like we're probably a long way from that, given that right now we're struggling to get past the moon. But I look forward to seeing what people come up with. It's going to be exciting.
Yeah. Well, I have one for the Star Trek fans too. I was thinking about deflector shields. These might be some kind of a solution. Do you think that there's any kind of electromagnetic shielding that could be used either along with traditional shielding or maybe in place of it, right? So that instead of going through all of these particles during interstellar travel, maybe they could be redirected around the craft in some way.
So from the radiation standpoint, that's kind of similar to how the Earth's magnetic field works, trying to do that. So definitely, like theoretically, definitely feasible. And I know that there's one company, I think in New Zealand, that is looking at using superconducting magnets to try and do some of these things. It's definitely a plausible solution. I think the concern you have is like, can you do it to completely get rid of all these problems versus is it going to get rid of 99%? And is 99% good enough? Those are the things you have to start thinking about is like, with problems like the one you're describing, it has to be 100% solution. You can't have a 99.9% solution. It has to stop everything. So trying to work out what's good enough is going to be difficult, but it's definitely a potential route. Yeah.
Well, there you go. I also wanted to touch on space colonies. I didn't want to neglect that because for the moon, Mars, or other planets without an atmosphere, or at least without appreciable atmosphere, astronauts are going to pick up a lot more cosmic rays. So in movies, habitats are usually above ground, right? Which is a cost saving thing for filming movies. But in real world space colonies, they're probably going to be buried to reduce exposure, if I understand correctly.
So this is definitely something I'm less familiar with, but I am more than happy to speculate and then have other people correct me later on. I think in some places like Mars, I think there's a increased radiation field, but I don't believe it's high enough to actually be that hazardous to humans.
Mm,
So
okay.
potentially being above ground would be okay. But I think with a lot of these things, there's usually practical limitations. Like, if digging and mining versus putting something on top of it, I think a lot of the time it comes down to what's the easiest thing to do first, and then thinking about the longer term solution afterwards. And there's an awful lot of work on on suits and spacesuits as well to kind of like use specialist materials that help with things like this as well when you're outside and getting exposed. But with these kind of like colonies, I think the biggest concern would be getting there, like you mentioned before. Like getting there is the biggest thing. Once you're there, it's kind of less of a problem. But longer term, if people are trying to live on Mars, which is bit of an out there concept right now, is going to be, there's going to be a lot of things you have to think about from like a food, water, and radiation standpoint. Everything's going to factor in. There's a lot of things.
Matthew, thank you so much for your time today. Let me close by asking if radiation exposure will prevent or seriously curtail future human space exploration, or is the work that yourself and your industry colleagues doing, is that work leading to solutions today that will help us tomorrow?
There are a lot of people. So I don't specialize in humans. There are a lot of people that really do specialize in that. So I think a lot of the work going on is gonna help with that. There are companies developing specialist materials for spacesuits to help with radiation, with protecting them from radiation when they're traveling to places. And there's also, like, really interestingly, quite a lot of the facilities that I try to go to and do testing with commercial companies won't accept me because I'm trying to do commercial stuff with electronics. And they're like, no, we're this huge particle accelerator, and all of our spare time is dedicated solely to like biological experiments, which a lot of which are based on like space travel. So there's a lot of work being done on that at a high level at universities and institutions. So there's definitely a lot of work happening, and it's probably going to be pretty positive.
Wonderful. Thank you again so much for your time today, sir.
Thank you. This was fun. Appreciate it.